Hi everyone, we meet again at this so-called e-lecture. So even though you can't see my face, hopefully this might bring some beneficial input to you to understand on the subject matters. So for this lecture 4 is actually consists of two parts. So the first part will we cover the aspect of ray pass in layered materials. So more or less it's just like a continuation from the previous lecture, but a bit more details. So while the second part will be about wave attenuation and amplitude, hence just like before, the second part will be covered in the normal class hour. So here we're going to recall what we have learned before. It's about Snell's law. So we have two parts actually, refraction and reflection. So we're going to focus on the refraction first. So for the refraction, the equation will be sine theta 1 over sine theta 2 is equal to velocity 1 over velocity 2, where sine theta 1 is actually representing incidence angle, while theta 2 is refraction angle equal to velocity of incidence medium or layer over VR is velocity of the refracted medium or refracted layer. So here we move to the reflection. Okay, since there is nothing to do with V2, we're going to cancel the V2 over here, while the V1 is identical for both sides for the incidence angle and reflected angles. So we're going to have this kind of equation where the incidence angle and the reflection angle will be identical or the same. So as far as the incidence and the reflected or refracted wave are concerned, we only consider the ray that hit the layer of V1 at the incident angle and resulted reflected and a refracted ray the same type of wave, which is a P wave. So let's say the P wave strike at this point, it will produce actually a P wave of reflected rays and P wave of refracted wave. So the question is, how about when the S wave strike the layer? So do the S wave will only generate reflected S wave and refracted S wave? So this will be a bit complicated, but I'm going to make sure that you understand this before we move to the next slides. So look at this illustration. So it is actually whatever wave, either S wave or P wave, that strike any difference in velocity medium, it will create disturbance. So these four things we call it as disturbance that will give rise to reflected P and S wave, as well as a refracted P and S wave. So regardless what type of wave that strike this medium, at this point it will produce refracted P and S wave and reflected S wave. So let's say S wave that strike to this point, it will actually produce S reflected and P reflected wave, and it goes to the refraction, P refracted and S refracted. As simple as that. So we take an example for the reflection case first. After that we move forward to the refraction. So the first figure, the upper figure here, is showing when only the P wave strike the interface between V1 and V2 layers. Here it will generate two type of rays, which are P wave ray and the S wave ray. As far as the velocity is concerned, the P wave is always faster than S wave, hence the angle of reflection S wave will always lower than P wave. So according to the Snell's law of reflection, the angle of incidence will be the same as angle of reflection depending the type of wave that strike the interface. So that when the P wave here is striking the interface, the angle of reflected P wave will be equivalent to the angle of incidence. While for instance, when the S wave strike the interface here, for this figure, the angle of incidence will be equal to the angle of reflected S wave. However, it's still obeying the rule where the angle of reflection of P wave is always greater than the S wave regardless. So here We move to a simple calculation involving the Snell's law, which is sin's incidence angle over sin's reflection angle is equal to V1 over V1, since the reflection is only considering and propagate in the layer of V1, then we only take V1 layer into consideration. So given V1 here for P wave if is 1500 meter per second, and for the V1 for the S is 900 meter per second at a incident angle of 20 degree. So let's say we don't know the angle of reflection of the S wave, because we need to consider it is unknown, whereby the P wave of reflection angle is identical, since it is equal to the incidence angle. So it's obey the rule that I mentioned earlier. So by inserting all the necessary values into the equation here, we will get this kind of form. So sinus 20 degrees over sinus reflection of S wave is equal to 1500 over 900. So the value that we will get is from this equation is about 11.84 degrees, or more or less equivalent to 12 degree. So let's see on the next figure for the when the S wave strike the interface of layer 1 and layer 2. So again it's producing just like what happened to the figure above. However, this time the angle of incidence is actually equal to the S wave reflection, since the S wave is the wave that strike the interface, meaning that this time S wave reflection angle is known while the P wave angle is unknown. So we need to consider that we don't get this kind of information yet. So by using the same formula, we're going to insert all the values, all the necessary values inside the Snell's law. So this is what we will obtain, where the angle of reflection for the P wave here is 35 degrees, and yes, is greater than the incidence angle of the S wave and reflected S wave. Now we move to the refraction. As aforementioned earlier, regardless the type of wave, when the wave ray hits the interface, it will generate two types of refraction, which are the S wave and the P wave refraction path. So for example here, the first figure, the P wave ray strike the interface at 20 degree and being refracted at the V2 medium and producing two angle of refraction ray paths, which are P wave refracted angle and S wave refracted angle. So this time none of them producing a refracted angle, which are not similar to the incidence ray path, because they are passing through a different medium, which is V2 medium. So given that the P1 or V1 of the P wave is 1500 meter per second, and V2 of the P wave is 1400 meter per second, and the V2 of the S wave is 2400 meter per second. Now our purpose is to identify the angle of refraction of the P wave and the S wave. So we need to consider that we still don't get this kind of information yet. So by using the Snell's law, we're going to insert all the given information to identify the uncertainties. So we go to the reflection angle of the P wave first. So here it will become this kind of equation: sinus 20 over sinus theta P wave refraction is equal to 1500 meter per second over 1400 meter per second. So the result will be more or less 66 degree of the P wave refraction angle. So similar goes to find the S wave from the Snell's law. Just replace 1400 with the 2400 meter per second, and the answer will be more or less roughly 33 degree. So the same concept will be applied to calculate for when the S wave strike at this point, just insert all the necessary information into the Snell's law equation, and here you will get this kind of answer. So all in all, what we can understand from here is whenever type of wave strike the interface, it will be at least producing these 4 type of wave dispersion, 2 in reflection, which is reflected P and S wave, and 2 in refraction, which is refracted P and S wave. So angle of reflection and refraction depends on angle of incidence, meaning that if you change the angle of incidence, the resultant ray path will be different as well. So same goes to the velocity of 2 layers. The angle of incidence will be varied as the velocities of the 2 medium is different. However, one of the important thing that you should take note is the S wave, however, will not produce a reflected and refracted P wave whenever the wave is in S, H or horizontal mode. So this is because the particle motion confined to the horizontal plane, like here, which is parallel to the velocity discontinuity. So this will cause no reflection and refraction of the P wave. So here is the table showing the relation of angle of incidence of the respective P and S wave, as well as the resultant angle for each wave for the respective velocity of layer 1 and velocity of layer 2. For example, look here, for the case of angle of incidence of the P wave, when it is 10 degree, of course reflected of P wave will be 10 degree as well. Reflected S wave will be more or less than reflected of P wave. And if you look at the incident angle for the S wave case, when it is a 10 degree or 11 degree, we take a look on the 11 degree, reflected S wave will be the same, which is 11 degree as well. Reflected P wave will be more or less a bit higher than reflected S wave, as it follow the rules where reflected P wave is always greater than reflected S wave, regardless the type of wave. So move on. We move to another part where we call it as critical refraction. So this is very important in the seismic refraction survey, so please take note on this. If you recall the behavior in refraction, at certain incident angle, one of the resultant ray paths will be 90 degree, meaning that it will be parallel to the interface or the surface, like here. So at a certain angle, it will travel along the V2 surface. So this incident angle, we call it as critical angle, and it will be a simple equation as sinus 90 is equal to 1, since it's 90 degree to normal. So now the transmitted wave is called then as the head wave. So this is what we call it as the head wave, and can be visualized these critically refracted rays as following. First, it's travel along the interface. Second, it will produce a disturbance of the interface. So this is the thing that it will goes up. So this is the energy or the wave that will bring the information of this layer upward. So if a refracted goes downward, it will not be captured by the geophone. So this disturbance is actually generate the second wave front. So here certain aspects need to be understand in this critical refraction. One, it acts as a source for a new secondary wavefront. Look at here, when the wave strike at this point, it will create a new wavefront and ray pass, and it will exit back to the surface at the critical angle. So at the critical angles only, the wave will bring the information of this layer underneath towards the surface, meaning that it will return the energy back to the surface and traveling upward at velocity v1. So this is v1 and this is v2, so it's traveling upward at velocity v1, and this wave we call it as head wave. So this head wave again is the one that responsible to bring the information of the v2 layer to be recorded by the geophone. So that is why head wave is something that we need to focus on and take account for the seismic refraction survey. As for the critical angle, the first figure here showing the normal reflection and refraction of the resultant ray path after being struck, after the ray path strike the v2. So it's normal, it will produce these two type. However, as the incident angle increase and it will hit or it will reach the incident angle of critical, so the critical angle will be travel along the layer of the interface of v2. So this is known as the head wave, and it also will produce the reflected wave. But here it will only produce the head wave, but no transmitted or no refracted wave passing through the v2, only on the surface. So for any value which greater than the critical angle here, no refraction or no refraction will be appear underneath, and the wave will be totally reflected, just what we has been shown here. So here we're going to talk about diffraction, where diffraction is very important in seismic survey. So diffraction is actually a seismic wave strike and irregularity, and the feature act as a point source and radiates wave in all direction in accordance with High-in principle. For example, just like this figure, so let's say this is the water wave that encounter barrier containing a slit. So here is the barrier and we have a slit. So this parallel or a planar waveform of the water moving towards this direction and hits the barrier and passing through the slit. So this is how the waveform will looks like, where it will semicircular moving towards this direction, and we can say that the ray path is moving many in all direction. So here again is a bit more detailed. So wave with planar wavefront. So it encounter barrier containing a slit with a dimension similar to the wavelength of the wave. So this is when d is equal to lambda, and the diffraction will be occur, and the wave spread outward to many direction from the slit in the semicircular pattern. So take note that as the size of the slit in the barrier is increased, the diffraction effect is also will be is not increasing, but it is decreasing, and is hardly detectable when the slit dimension is more than the wavelength. It's several times more than the wavelength. So we suggest that diffraction will be most important when sharp changes in curvature have a radii that are similar in dimension to the seismic wavelength. So common sources of diffraction in the ground includes the edge of fault layer, small isolated layers such as boulder in otherwise a homogeneous layer, and pinch out. So this is how the diffraction phenomenon will be happen. So when the wave energy strike the discontinuity in subsurface interfaces, diffraction will be occur, and the seismic wave bend around to many direction after it hits the discontinuity. So it will scatter the energy from all direction, and it will goes backward and upward many direction toward its source. So this point will consider a new source. So it is obeying the High-in principles. So this is the first source. When it hits the discontinuity, it will produce a secondary source that goes to many direction, upward and downward. So okay, now we will go a bit to a seismic survey. So compressional wave have the greatest velocity and always arrive first to any points. So that's why it's easier to only count the P wave information rather than the other wave, again because the P wave is always the fastest wave, and the first wave that will be arrived to the signal recorder. So however, in certain cases, shear wave is very beneficial and rather important, especially when it comes into geotechnical engineering purpose. For example, assessing foundation, pavement and construction. So here we have a general diagram that shows how the 2D seismic survey works. We actually have several recorder that will be aligned into a single spread, and the shot will be most of the time on land is by using hammer, so it will give some impact inside and outside of the spread. So for this case, however, we will only using a hammer and a signal recorder at certain distance to explain the basic of the survey's concept. So when the impact is produced from the hammer, four types of compressional wave will be produced actually, namely air wave, direct wave, reflected wave, and the head wave. So the only surface wave that will be recorded in the seismic section is the ground roll, where the love wave is really hard to determine, but ground roll is the one that will be appear obviously. So air wave is a wave that will travel on the air. So direct wave is a wave that propagate along or just below the surface. Reflected wave is when the wave made the contrast in acoustic impedance and it travel upward, so it actually will hit at any point. When it meets the higher velocity layer, it will goes outward and reflected upward. However, in order to be captured by this recorder, the reflected wave need to be goes into this point, and head wave and refracted wave will be produced on the surface at the higher velocity layers. So here is a picture. We call it as a shot gather section. So when you have a several series of geophone, so let's say you have this 24 geophone here on the y-axis that were planted in one straight line with a fixed interval distance, and the x-axis here is the time domain where it will record the rebound signal. So this kind of basic feature will be generated as the source is close to the receiver number 1 and the furthest is geophone number 24. So that is why the arrival for each geophone is varied and will be delayed as it goes to the further geophone. And take a look on the geophone number 1 here. So here is the signal rebound. So this is the first time arrival. So the arrival of signal at the geophone 1 is the fastest, while the geophone for the geophone number 24 is the slowest. It will be delayed due to the offset increase. So since the geophone number 1 is the closest one, it will get the signal first, and since the geophone number 24 is the furthest one, it will get the take a longest time to get the signal. So 4 identical wave signal can be recorded actually for this short gather section, and it represent in a coherent form, like here. So this is what we call it as coherent form or linear form, because if you can see the pattern when it goes downward here, it looks like a linear or coherent form. So this actually the direct wave signal, where it will be the one who arrive first. Here is the direct wave that will arrive first. After, however, at some distance, the direct wave will be superimposed by the critical refraction head wave, and can be recognized by the change in slope or gradient. If you look here, this is the slope of the direct wave, but here at the geophone number 13, the slope is changing, I mean the gradient is changing. So here is the direct wave arrival, where the direct wave will take place, the first rebound. So here we have another two or another three coherent form. One is reflection, air wave, ground roll. Air wave is very easy to detect, where it will be always the slowest. I mean the slope will be always the steepest one, followed by the ground roll. And the reflection is always the signals that will be appear in what we call it as a parabolic form or hyperbolic form. I mean the form of a curvature form. So it will always appear in the region of the air wave and the critical refraction or head wave. So moving on, an easy way to gain some initial insight into distribution in time-space of the arrival of this wave of the surface is construct a spreadsheet form and analyze by placing them into a graph. So this is what I'm going to explain during the lab, so you don't have to be worried. So this is actually how we're going to conduct the lab, when you need to take all the necessary information and plot it into a graph. So that's all for lecture 1. Lecture 4 part 1, I'm going to continue lecture 4 part 2 in the normal class hour. Thank you.